Welcome to Homework 8 Solutions video. All right, so let's start as any reasonable person would start at number 1. And we'll talk about the partial derivatives of the following function. Xy squared z cubed minus sine xy plus e to the x z squared minus tan of y to the 10th z over ln of yz to the 5th. Okay, so take a look at part A, which says the partial derivative of f with respect to x. And this is also sometimes denoted as f sub x, but I think in this case, this is probably a little bit more illuminating, and you'll see why in parts B and C. But feel free to denote it like this. This is fine. Okay, so what this says is take the derivative of f with respect to x, right? This is now sort of the variable that we're looking at, and everything else is a constant. So what I'm going to do is I'm going to circle the constants. And I'll rewrite the function to sort of mimic this, because remember that when we're looking at something like this, like just a regular function with one variable, we typically don't write x squared times 4, right? We'd prefer to write 4x squared. We take the constants and put them out front. So that's what we're going to do. So I want to rewrite this as the partial derivative with respect to x of the function written as the following. And I think this is probably a good habit to get into, at least for your first few times doing partial derivatives. I think it makes it a little bit more clear. What the derivative should be. Okay, so I have a constant times x. So I could really think of this as, typically I think of it as like 2 times x. Anytime I have a constant, I usually just call it a 2. So it appears, but it's still a small number. So what's the derivative of 2x? It's just 2, right? I bring the power of 1 down to the front, and then I drop the power to 0. So x to the 0 is 1. 1 times 2 is 2. So I get, I'll make a little bit more room here. So I get, for the first derivative, y squared z to the 3rd. Okay, now this is like sine of 2x, right? And to do this derivative, I need a chain rule. So what's the derivative of the outside? It's cosine. I should use, sorry, that should be yx here, right? Times the derivative of the inside. And what's the derivative, partial in this case, of yx, or 2x? It's just the y. It's just the constant, right? It's just the constant coefficient. So times y. Same thing here. I need a chain rule. This is e to the z squared x times the derivative with respect to x of the exponent, z squared x. In this case, it's just z squared, right? It's just the coefficient. This is just a linear term, x to the first, bring the power down, drop it, so on and so forth, right? We've seen this already. And this guy, notice I circled the whole thing here because there are no x's involved, right? So this guy goes to 0. This is like a 2, right? Derivative of 2 with respect to x is just 0. The derivative of a constant with respect to x is 0. So this is my final answer for part A. All right. So now building off of that, I have the second derivative of f, the second partial derivative of f, dy dx. Now, you'll remember from the video, I hope that you would remember from the video, that this really means the derivative with respect to y of the derivative of f with respect to x, right? If I just sort of multiplied together using the notation that I have d times f. If you're thinking about these as multiplication, it's not really, but this is where the notation comes from. D times d gives me a d squared on top. And then on the bottom, it's just dy dx, sort of concatenated, right? Just thrown next to each other. So just like with composition of functions, I have to read these things right to left, meaning I plug in h first, then I plug this into g, then I plug this into f. So I read it right to left. In this case, I do the derivative with respect to x first, right? I have to figure out what this thing is. Then I can take its derivative with respect to y. So I read this right to left. Now, you'll also remember that either order will give you the right answer, and that's absolutely correct. However, if we write it in an order like this, your best bet is to read it right to left, because this is the correct way to read it, and we've written it that way for a reason. In this case, if you try to do the derivative with respect to y first, just taking f and taking the derivative with respect to y, this term that I have circled over here becomes a giant mess. You have to do a chain rule with a quotient rule and product rule and all kinds of crazy stuff involved in here. But if you do it with respect to x first, this whole thing goes to 0, and I have a much easier thing to work with. In fact, in the example that I have, I already know what df dx is because I've done it here, right? That was part A. And this is why the problem was phrased in the way that it was. So I take the derivative with respect to y, partial derivative with respect to y, of the function I just found. Okay, and we can do that. I treat everything that's not a y as a constant, so I'll circle this. I won't rewrite it this time in the other order. You can do that if you like. But okay, so I get 2z cubed y minus, and here I'm going to have a product rule, right? So I have cosine xy times 1, the derivative of y, and I'll put this in parentheses here, plus y times the derivative of this. So cosine gives me a negative sign of xy, but there's a chain rule involved, so I have to multiply by the derivative of the inside with respect to y, and in this case it's just x times. Great. And this thing that I've circled here, again, is just a constant. There's no y's involved, so it just goes to 0. This is what I have, and I'll simplify a little bit, make it look a little cleaner. 2z cubed y minus cosine xy plus xy sine xy. Okay? And then finally, the third derivative is the same sort of thing, that we did before, right? I take my previous answer and I take his derivative with respect to z. Okay, so I'll box this because this is our answer for part B. And now how we take a derivative with respect to z, well, there's no z's here and there's no z's here. So these are both going to go to 0. And I have sort of a separated constant in this case. I'll try to circle it like this. 2y is my constant term, so I'll rewrite this. d dz of 2y z cubed minus cosine xy plus xy sine xy. The only term with a z in it is my 2yz cubed, so I bring the power of 3 down. I get 6y z squared. 6y is the constant that has to stay. I take the 3, multiply it by the 2, it gives me 6, and I drop the power. Cosine xy has no z's in it. That goes to 0 because it's the constant. Xy sine xy goes to 0 because there's no z's in it. And there we are. Okay, moving on to number 2. I have k cubed minus l to the 6th equals 2kl to the squared. I'm sorry, squared. L is a function of k, and we want to find dl dk. All right, so L is implicitly a function of k. So we could do this the long way, or we could use the shortcut, and I would recommend using the shortcut. So I need f of kl to equal a constant. Oh boy, constant. Okay, so that just means bring everything with a letter involved over to one side. And in this case, there are really no constants besides 0. I keep writing a 6 there. So I just have this. And this thing here is my f of kl, right? And it equals a constant. So we're good. Means we can use the trick that says dl dk equals negative f sub k over f sub l. Or using the notation of the last problem, negative df dk over df dl, with the d's being, of course, the scripty d's, meaning partial derivatives. This, notice here, this is a standard English d, whereas this is the scripty del, right? So when you're asked to do something like this, when there's two variables involved, and you're asked to find a derivative, and they are straight up and down regular old English d's involved, that means you have to use implicit differentiation. When you see a question which asks you for a derivative with this scripty d, it means you're doing partial differentiation. Right? So that's, even without explicitly asking or telling you which method to use, you can still figure it out based on the notation. That's why there's differences in the notation. Okay, so we just have to figure out what is f sub k and what is f sub l. All right, this shouldn't be too hard. F sub k is 3k squared. It affects this k cubed because, of course, we're taking a derivative with respect to k, and I will actually, let me write out one more step here. Derivative with respect to k of k cubed minus l to the 6th minus 2kl squared. Okay, so this is just a function of k, so we get 3k squared, just like a normal derivative. This l to the 6th is a constant, so he goes to 0. So I'll write minus 0. You don't have to write this, but I'm writing it just to emphasize where this comes from. And in this case, 2l squared is our constant and k is our variable. So I just have 2l squared as my derivative in this case. So this is 3k squared minus 2l squared. Okay, and now I take the partial of k cubed minus l to the 6th minus 2kl squared with respect to l this time. K is just a constant, so he goes to 0. L to the 6th, that's an easy derivative. 6L to the fifth, just the power rule. And in this case, 2K is our constant. This is the only thing attached to this term which has nothing to do with L. So I bring the 2 down, apply power rule, 4K, because the 4K is a constant, it has to stay in some form, times L. So this simplifies to negative 6L to the fifth minus 4KL. All right, so our final answer is dl dk is negative fk over fl. Negative fk is negative 3k squared minus 2l squared, all over negative 6l to the fifth minus 4kl. And I would say that's good enough. I don't think anyone will bother you from not distributing that negative or canceling anything. Great. Question 3. We take a look at it. We're looking for the derivative with respect to x, and these are regular English d's of x plus 1 to the 3x. Okay. Now the hint says, oh no, I'm sorry, there is no hint for this one. So it should be obvious to you, or at least after thinking about it for a little bit, that you need logarithmic differentiation. So this is something like, recall, when we were doing L'Hopital's rule, these were the sort of the really hard problems where we had something of the form x to the x, something like that. You don't need that, I don't think. Maybe you do. I don't remember if you need this plus or not. So we had this, and this was of the form 0 to the 0, and this was indeterminate. So what we had to do was set it equal to y, then take the natural log of both sides. Then we had x ln x. And then this was a product, which is something we can work with. So this was 0 times infinity in this case. And then from here on out, we did the standard trick, applied L'Hopital's rule, so on and so forth. But the idea here, at least for these first two steps, first one step really, is exactly the same. It's that exponentials are really hard to deal with when the variable is not only in the base, but also in the exponent. If this was a constant, we know how to take a derivative. If this was a constant, we know how to take a derivative, right? This is just power rule if this is a constant. And if this is a constant and there's an x in the numerator, it's just an exponential rule. But here I have an x in the base and an x up on top. And that's the same situation here. I have an x in the base and an x up on top in the exponent. So how I deal with that is, well, I have to turn it into a product because I want to get everything down to the ground level so I can do stuff with it. Products are nicer than exponents are. So what I do is I set x plus 1 to the 3x equal to y. Okay, now I take an ln of both sides. ln of x plus 1, put that in little parentheses, 3x there, equals ln y. Okay, now the reason I do this is because I know my log rules. This gives me 3x times ln of x plus 1, right? Your mom wants to come down. Okay, so I have a product and I know how to do a product rule. It's not great, it's not my favorite thing to do, but I can do it much more easily than I can do this, right? So it's not ideal, but it's better. Okay, now notice that if y equals this thing, all I'm looking for is dy dx, right? I'm looking for the derivative of this function with respect to x. Well, I've relabeled this as y. I'm just looking for the derivative of y with respect to x, dy dx. Okay, so I can use my tools of implicit differentiation to solve this thing. So let's take a derivative of both sides. I'll write this, d dx. Right? Derivative is like any other operation. As long as I do it to both sides, I should be fine. Okay? So this gives me a product rule. All right, I can handle this. The derivative of 3x is just 3, and I'll keep the second guy the same. Plus, the derivative of the second thing is, well, I'll leave the first thing the same, 3x times derivative of the second thing is 1 over x plus 1. And then I guess I have to multiply by the derivative of x plus 1, but that's just a 1, so I'm just going to ignore that. Now, the derivative of this, I have to use implicit differentiation for. And I know implicit differentiation is a long phrase, and it's not really, it's not very intuitive what's going on. But remember from the video that implicit differentiation is exactly just the chain rule. So I will not call it implicit differentiation. I will call it the chain rule because that's all I'm doing. So I take the derivative of this, right, which is 1 over y. But y is a function of x, right? Y is not an x. That's the important thing. Y is not an x. So in order to correct for me assuming that I could just do this, I have to multiply by the derivative of the inside. I've taken the derivative of the outside, 1 over whatever's on the inside, multiplied by the derivative of the inside. And that is exactly dy dx. This exactly says derivative of y with respect to x. And y is the inside. So this is what I have. And now I want to solve for this. Meaning just isolate it, right? Use algebra, treat this as its own symbol, and isolate it. So I have, well, how do I get this by myself? By itself, I just multiply both sides by y. All right, so I get y times this big thing, 3 ln x plus 1, plus 3x over x plus 1 equals dy dx. And one last thing I should do is replace y, because if I can write this whole thing as a function of x, meaning just having x's in it, no y's, then I should do that. That's definitely a good idea. Sometimes you can't do that, but in this particular case, you definitely can, because I have an explicit expression for y. So I have x plus 1, I keep drawing parentheses, x plus 1 to the 3x, which is just substituting in for y, times this big thing, equals dy dx. And that's good enough. You don't need to distribute or anything like that. There's not going to be any simplification that you can really do here. But yeah, I mean, this is the method you use every single time, and this is in fact just the general formula. So there's a nice sort of form of these things. You're always going to have a y on the outside and then a derivative of a product on the inside. So when you're checking your answer, you should have something like that. Okay, so number 4 is the one that came with a hint. Derivative with respect to t of the following: t squared plus 1 over, or times t minus 3 minus all over the square root of t minus 2. Okay, and now the hint was to use logarithmic differentiation. Now, the reason we gave a hint here and we didn't for the previous one, because we used logarithmic differentiation on the first problem, or on problem number 3. But here, this is a problem I can do without logarithmic differentiation. Right? We just have to use quotient rule with a product rule, with a chain rule, and all sorts of stuff. So I could do it, but it's a lot more complicated. instead, we're going to follow the hint and we're going to use logarithmic differentiation. And you'll notice how much easier this gets. So let's again set this big thing equal to y. Okay, and now again, I'm looking for dy dx, right? Y is a function of x, or I'm sorry, crap, that should be t. dy dt. Y is a function of t, and I'm looking for the derivative of this function with respect to t, okay? So we take the natural log of both sides, and the reason we do this is, again, because we know our log rules, and log rules actually make things better. And it will make this derivative much easier. So using my log rules, what I want to do is decompose this inside into a bunch of terms that are easier to take a derivative of. So let's do that. Using the, I don't want to call it the quotient rule, but the difference rule, I guess. I take the ln of the top minus the ln of the bottom, right? You'll remember this from the beginning of the semester, hopefully. And the right-hand side doesn't change because I'm just applying log rules over here. And this one has a sum rule, t squared plus 1. Crap, that should be plus ln t minus 3 minus ln square root t minus 2. Okay, but there's one more thing I can do, so I don't have to worry about a chain rule on the inside. Still have t squared plus 1 and t minus 3 on the inside over here, because there's nothing I can do. When I have a plus or a minus on the inside, there's nothing I can really do. But here, I have a power of 1/2, right? Remember, I can write a square root. I can write a square root as to the 1/2 power. So I apply the third log rule, the one that says your mom wants to come down. And I get this. Okay. Now, just like before, I take a derivative of both sides. d dt of this whole big thing. Like so. All right, and I'll come up here and try to write it up here, and hopefully I won't run out of room. All right, so now taking a derivative here is a little bit less complicated, right? There's 3 things I have to do, but it's really only chain rule that I have to do 3 times, not quotient or product rule, which is, it definitely makes life easier. So I'll separate that out. And what do we get? We get 1 over t squared plus 1 times the derivative of the inside, right? Just by chain rule, I treat this as if it's a t, and I take a derivative, 1 over the inside. Then I multiply by the derivative of the inside. So this is times 2t. Plus, and I do the same thing here, 1 over t minus 3. That's terrible. T minus 3. Multiplied by the derivative of the inside, but in this case it's just 1, so I'll ignore that. Minus 1/2 times 1 over t minus 2. Okay, and same sort of chain rule here. I get 1 over y times dy dt. This is very similar to what we did for problem 3. Okay, so what do we get? Well, we get a whole big thing multiplied by y. So I get 2t over t squared plus 1 plus 1 over t minus 3 minus 1 over 2 times t minus 2 equals dy dt. All right, and again, I can replace y with this big thing so that my left-hand side only has t's involved. So my last step is replacing y. And of course, we would never ask you to distribute through. That would be a waste of your time taking the exam and certainly a waste of our time grading the exam. And here's my final answer. So in this sort of a case, when you have the derivative of a big product with square roots and powers and all sorts of crazy stuff, it's often a good idea to use logarithmic differentiation. It's not required. However, doing this using chain rule and product rule and quotient rule would take, I would guess, probably twice, maybe 3 times as long. And there's a lot more opportunity for mistake. So it's just a convenience thing more than anything. So question 5. Finally, we have bike pedals cost $20 each. We have brake pads cost $5 each. A equals number of pedals bought, and B equals number of brake pads bought. And we want to determine the quantities of pedals and pads which maximize and minimize utility function. U equals 8a squared plus ab plus b squared. And give max and min values of utility. Okay, so there's a few things we have to do here. But I would say the important information is here and this whole grouping of things here. Right? Okay. And of course, the problem also says to use Lagrange multipliers. It's not necessarily the case that we'll tell you to use Lagrange multipliers. We probably will, but you should notice that if there's a function of multiple variables, that you're going to want to do Lagrange multipliers if it applies. Okay, so first of all, we notice. Oh, I forgot to write down one more thing. I'm sorry. We spend $1,000. So that's another piece of important information. So because we spend 1,000 and the cost of bike pedals is 20, cost of brake pads is 5, and we have these variables already defined, we have our constraint equation already. Right? This is 20A plus 5B equals 1,000, right? Because if I sell A amount of bike pedals at $20 each, well, the total price for A of them is 20 times A, and similarly with B. This is the total amount that I'm spending, and it has to be equal to 1,000, right? Just by what the problem tells me. So this should be something that you can pick off, maybe not immediately, but pretty quickly and once you have enough practice reading these things, you'll be more comfortable. And the optimization, the function, yes, function, is utility, the thing that they give us and explicitly tell us to optimize. Okay. All right, so first things first, I have to get my constraint equation equal to 0, so I have to rewrite it. So rewrite constraint. Boy. Okay. 20a plus 5b minus 1000 equals 0. All right, now that I have this, I can write out my Lagrangian, L of a, b, and lambda. So I get what? The utility equation, which is 8a squared plus ab plus b squared minus lambda times 20a plus 5b minus 1000. Okay, now let's take our partials, and I'll write them like this. I think generally people prefer that notation. It's a little less daunting. So I get 16a here plus b minus 20 lambda a, and I set that equal to 0. L sub b, I get a plus 2b minus 5 lambda b. Oh, I'm sorry. No. This should be, sorry about that. Not a, just 20 lambda and 5 lambda in this case, equal to 0. And L sub lambda is negative 20a plus 5b minus 1000 equals 0. Okay. All right. So let's get a new page here just to organize a little bit better. So I have 16a plus b minus 20 lambda equals 0. L sub b is a plus 2b minus 5 lambda equals 0. And L sub lambda is just our constraint, 20a plus 5b minus 1000 equal to 0. Okay, so using this, I solve for lambda. So I get 20 lambda equals 16a plus b. Oh, 16a plus b. Oh, no, of course, yeah, duh. What am I doing? Undo. Yeah, 16a plus b. I'm going to write that not like an idiot. Thinking I'm dividing by 20 already. Now let's divide by 20. So I get lambda equals 16a plus b over 20. And I saw some students tried to reduce this, but of course you can't cancel anything with the 20 unless you can factor it out of both terms on the top. And since b doesn't have any coefficients other than 1, you can't really factor anything out. So this has to stay how it is, but that's fine. Over here we get 5 lambda equals a plus 2b. So solving for lambda, I get a plus 2b over 5. Okay. So let's bring those together. I'll try to keep this somewhat organized, and I'll just bring this down here out of the way so it's a little less cluttered. I get 16a plus b over 20 equals a plus 2b over 5. Okay, so our numbers are going to get a little big here, but not terrible. So that's going to be 80 there, right? Because 5 times 8 is 40, and 8 times 2 is 16. So it'll be just 40 times 2 gives us 80a plus 5b equals 20a plus 40b. Okay, this is fine. So I get 40a, or yeah, listen to me. Subtraction gives me 60a equals 35b. All right, it looks like I could solve for either one here. So let's just say A equals 35 over 60. B, and I can reduce that a little bit. Looks like a 5 comes out of each. So again, a 7 on top. And how many times does 5 go into 60? 12. So 7 over 12, B. Great. Okay, so I have a substitution to use for my A, and I'll plug that in. So this turns into, and of course I'll just get rid of the negative, multiply by -1 on both sides. So I have 20 times 7 over 12b plus 5b minus 1000 equals 0. 20 over 12 reduces to what? This is 5 over 3, it looks like. Right, because I could take a 4 out of each. So this is a 3, this is a 5. So I get 35 over 3b plus 5b minus 1000. I could do even equals 1000. So adding these two together, I get 35 plus 15 because this is, well, I'll just write it. 35 over 3b plus 15 over 3b equals 1000. Combining these, I get 50 over 3, I believe. Yep, that seems right. Equals 1000. Okay, so now just solving for b, 3000 divided by 50. So you can cancel a 0. 5 goes into 36 times, so of course it goes into 360 times. So b equals 60. All right, that's one of our critical points. And that leads us to conclude that A is 7 over 12 times 60. All right, well, this is manageable. 60 over 12 reduces to 5 over 1, so A equals 35. Okay, so I have one critical point, and I'll label that here. Critical point is in the forms A, B. I have 35, comma, 60. And then it looks like that's the only critical point I get, right? Doesn't look like we've missed anything. We only get one solution. But we also have to pay attention to the endpoints, right? Because this is a real life problem, we have to, we have to be careful. If we're buying bike pedals and brake pads, we can't buy negative of those things, right? So let's look and see what our endpoints are. And again, these are going to be the form A, comma, B. So remember our constraint is going to be 20A plus 5B equals 1000. Okay, so what happens when A equals 0? What if we buy 0 of these things? Because that's the least amount of bicycle pedals that we can buy. Well, when A equals 0, B has to equal what? Well, 1000 over 5, or 200. Okay, how about when B equals 0? Well, then A has to be 1000 over 20, which is 5. Okay, so we have the endpoints 0, comma, 200, and 5, comma, 0. Great. All right, and that's all of the endpoints we have to worry about, because this is when A is at its maximum. A, of course, can't get any bigger because that would force B to get smaller, and that can't happen. And B can't get any bigger than 200 because that would force A to get smaller. And of course, that can't happen because A can't be negative. So in these problems, it's enough to check what happens when each variable equals 0. So I have the two endpoints and I have these. All I have to do is find out which ones maximize and minimize U, and what are the max and min values of u. Okay, and how do we test this? Well, we could use like a second derivative test or something like that, but that wouldn't really take into account endpoints, and this is an absolute min and max problem, not a local min and max problem. So the only way to do it is really just to compare outputs. So compare outputs. That is values of u. All right, so I take u and I plug in each of these points. Let's start just by going left to right. We'll plug in 35, 60, and remember the formula is 8 times a squared plus ab, which is 35 times 60, plus b squared, which is 60 squared. And I'm not sure what this is, so you can just use a calculator. If the numbers are, this big, then we don't mind if you use it. I'm sure you guys have figured that out by now. So I get, out of this term, I get a 9,800 plus 2,100, and 60 squared is 3,600. Okay, adding this all together, I get 15,500. Okay, so that's one of our outputs. Now let's do the endpoints, 0, 200. I get 8 times 0 squared plus 0 times 200 plus 200 squared. So that should give me just 4 with 4 zeros, or 40,000. And u of 5, 0 is 8 times 5 squared plus 5 times 0 plus 0 squared. So 5 squared is 25. 8 times 25 is 200. Okay, I've just noticed that this is 50 and not 5. And I hope that you were all screaming at me at that time to let me know that I can't do basic math. But this is fine. So I'm just going to change this. I'll make a little note in the video, and I'll let you know that this correction is coming. I didn't want to go all the way back and change everything because I didn't remember what I was saying and what was written before I wrote all this. So anyway, I don't get 200. I get, I believe, 2,000, right? Because this is going to give me 2,500. And then I get 8 times 2,500 actually would give me 20,000, I believe, plus 0 plus 0. So this is just 20,000, right? All right, sorry about that. So these are the things that I have to compare. I probably shouldn't have boxed them, probably should have circled them or something different. But now I just have to find what's the biggest and what's the smallest and what are the locations. So it looks like 0, 200 gives us the biggest. 35, 60 gives us the smallest. And we have those values. So max is 40,000 at the ordered pair AB 0, 200, and the min is 15,500 at, what was it, 3560 or 6035? 3560. Okay. Right. And this would be our final answer in this case. I can't draw a straight line. Okay.